Curious how quantum mechanics mirrors classical physics? Welcome, everyone. Today, we decode the Heisenberg equations of motion and uncover their significance in revealing particle behavior. Let's get started. We see here that we have the basic concept of the Schrödinger picture and the Heisenberg picture, which we touched on last video, via a basis change in the Hilbert space. But just to recall, this is all about the wave or state vector propagating or evolving in time. And in the Heisenberg picture, it's the observables or operators evolving in time. So that's pretty cool. But let's see what we need to do for this problem. In problem 6.29, we are tasked with differentiating equation 6.72 to obtain this Heisenberg equations of motion, and which is stated here. And for this, we're stating that q hat, which is the observable or operator, and h hat, which is the Hamiltonian, are independent of time, at least for this simplistic case. And then after that, we want to plug in for q the position and momentum operators to obtain the differential equations for the Heisenberg picture observables uh, xh, so position and momentum. Okay, in the Heisenberg picture for a single particle of mass m moving in the potential Vx. This will be important only insofar as what derivatives we use, so just keep that in mind. But of course, like we saw last time, we care about this because we're connecting a quantum with the classical. Well, we saw that there were two pictures here, but there's actually a third called the interaction picture. So the challenge today is what differs this picture from the interaction picture? Although we see that the Schrödinger and the Heisenberg pictures have some kind of parallel but yin-yang construction, one evolves in time, the other doesn't, and vice versa, that kind of thing. Where does that fit in with the interaction picture of both of these ideas? And this is important because the Heisenberg picture illuminates the connection between classical and quantum mechanics. And from that, we say that the quantum operators obey the classical equations of motion, as we'll see. But for this, just a reminder, there is a companion PDF to help you follow along because I did not include all the nitty-gritty in this video, so access that using the link below. And if you find value in this content, you can have a direct impact on its success by liking, subscribing, sharing with a friend, or donating through Buy Me a Coffee. No account required. But with that, let's dive into this question. Alright, cool. So stop number one, pretty simple. We're starting from equation 6.72, and we're trying to take a derivative. Okay, now recall that the equation 6.72 is nothing more than the transformation equation from the observable here into the other basis, which is the Heisenberg picture. We dealt with this all chapter long. No shocker there. Of course, we see here that this derivative acts on this operator, and we just set it aside. The real action happens over here on the right-hand side, where we have a product rule. Of course, thankfully, we're told that Q is independent of time, so we don't need to worry about having the triple product there, just of U of t and the adjoint. Okay, and you could see that highlighted here in the green and blue. From that, we have to take the derivative of each of these respective operators, but recall that equation 6.71 gave us the definition of the time evolution operator in terms of the exponential. Okay, so that's not too bad. We just take a derivative of an exponent, easy enough. But side of warning for this, when you're dealing with exponentials of operators or matrices, things like that, the rules are kind of weird, and this is a special case because of the properties that we've established here with the Hamiltonian. And I very much suggest that you go look at a differential equation or a linear algebra book. In particular, reference the Baker-Campbell-Hausdorff formula because that is very important for this, as we saw in question 6.27. That formula is a powerhouse in this theory right now, especially with the exponentials, the groups, the operators, all that stuff. That formula should be on your cheat sheet whenever you're approaching these questions. But Because we have the special properties, we see here that this eases up real quick, and we get this exponential back just due to the differentiation laws, which we know is the unitary, or not necessarily unitary operator, but the time translation operator. And we just get these constants out front. Pay special attention to the fact that there's an IH bar here because that'll be a common thing with this derivative and that derivative. So let's go check out what the adjoint derivative is and substitute them back in. So here's where we say that the derivative of the adjoint is the adjoint of the derivative. So we take this adjoint, put it outside, substitute everything in. We're good to go there. But realizing that applying this adjoint, it's the transpose conjugate. So this has to go to a positive sign. This has the dagger, which puts it over here on the other side due to rules of transposing. So this goes over here, and that's why we see it here. And again, all of that's in the PDF. Just it doesn't make sense to keep all those nitty gritty details here, but rest assured is in there. And then in this next step, I take the fact that they have an IH bar in both terms here and push it over just to clean up the simplification. Pretty easy there. But now, in order to simplify this derivative, we have to go back to the commutator relations. And this is because we know that if they are commutable, or that they commute, then we could switch the order and then rearrange it and actually see that we get a derivative of the operators in the Heisenberg picture. So let's pay attention to that as we substitute in. The big premise here comes from the fact that the commutator with the Hamiltonian and the time evolution is 0. And we showed this because in problems 6.27, we showed that after we break apart this commutator bracket via linearity, that the momentum operator and the time evolution operator, that goes to 0. So check out that if you want. The subscribers have it. But if you want access to it, feel free. If not, it's pretty easy to work out. Just be aware, this does come back into fruition a lot moving forward, so best that you learn a little bit about it now, or at least keep it in your commutator identity notebook. And then here we just see that scalars commute, so that goes to 0 too. So all in all, we know that this commutator relation equals 0, so the Hamiltonian and the time evolution do commute, and this gives us two things that we can use. Let's see what those are. All right, so we know that this also holds for the adjoint simply because the Hamiltonian is also its own adjoint, things like that. We've talked about that almost ad nauseum in chapter 3 about the properties of all these operators. So if it commutes with the time evolution, it also commutes with the adjoint. And again, go back to the fact that these are unitary operators. If you don't believe me, have fun with that. But the big picture item here is that we get this commutation relation of that HU equal UH, and then the daggers equal to one another. And here's where we can actually apply them. Let's recall that after the differentiation, we ended up with an equation like this. What makes this special is that we see here that we have a case where H is in the way of this operator acting on Q or sandwiching Q. And we know that from equation 6.72 that that would make it into a translated operator. So that's what we're trying to do. So we're going to substitute in this definition here with this, and then we see here that we were able to switch the order. Similarly, this H, this Hamiltonian, is in the way of this operator here, and we want to put it right there for the same reason. Okay, and then we could see we can do that from this relation here. Try color coding it so you can see that green goes to blue, blue goes to green, and we're good to go. Once we switch them around, and of course on the left hand side here, we're just tidying everything up, rationalizing the denominator to form match the equation that they want. That's not necessarily what you have to do, but it definitely is helpful just to get it all on the same page. And then you see I squared goes to -1, no big deal. But after we apply the fact that these operators are that they commute, we see that we get what we want in purple which is the expression for a transformed observable on both of these terms, which is awesome because we can now put in the definition of equation 6.72 and put in the fact that that is the observable in the Heisenberg picture, excuse me. And then of course, we multiply over that -1 onto the right-hand side that we saw from rationalizing the denominator. And once we distribute it to each of these terms, okay, we do that here, we switch the order, and this looks like a commutation relation. Thus, we get IH bar with the time derivative of the commutator of QH and Q sub H with this a T, because that's what the time evolution does. And this gives us the Heisenberg equations of motion. This is fascinating. This is the differential equation that we saw in the opening slide. Of course, if the observable is time dependent, then we have another factor to deal with, but we don't have that here. And so we get the results we want, and from this, we can create the two differential equations by plugging in x and p respectively. So now that this is done, let's dive into that and see how we simplify it down, because you'll definitely need more results later. Thus, this brings us to stop number 2, where we find the position differential equation. And of course, we see here that we're plugging in x hat for q hat, and we see here that just by simply plugging it in, we get everything we need to. Go back to equation 6.71, or excuse me, 6.71. Oh no, I lied, it's 6.72. One of the two. But plug them in, you see that this is the transformation equation, no big deal. But notice that now we have a commutator with a triple product here on H and then H bar on the other side. So let's reference our old friends from equation 3 or problem 3.14, which was the left-hand distributive property of commutators. Okay, and so if we just clump together these two things and call that A, for example, and this thing, call it B, for example, of course, hat for operators, we see that we get the A hat, B, or AB. This is AB, and this turns into C to keep the notation the same. Okay, so here we get ABC, then we get ACB, same concept. But again, that formula was shown and proven back in chapter 3, so may as well use it. But now notice that we have a commutator right here that has a product here, so we have to apply the identity again, and that leads us straight to this thing. And you see we have our little friend UT here in green that needs to be right-hand distributed into the parentheses now. So let's go ahead and do that in order to simplify. All right, so we see that we distributed UT into that set of parentheses, but we just showed here that we saw that U and H are commutable, so the commutators are 0, 0, 0, and of course 0 times what they're multiplied by gives us 0. Voila, we get a fantastic cancellation. Cool, we can deal with that. So our highlight focus is here on x hat and the Hamiltonian, which of course we revisited in problem 6.27, as you see by that's how to transcribe this underbrace. But with that, we saw that we got an IH bar over M with the momentum. Cool. We see that the IH bar here and the IH bar there cancel out wonderfully, and we're just left with something 1 over M with a U dagger, an observable, and another U. This is a transformation equation, so we can write P hat in the terms of the Heisenberg picture. So we just successfully found the x differential equation, which of course relates to momentum. Take the time derivative and you're good. And of course, we'll see how this really looks here in a second. Of course, this propels us straight to stop number 3 for the momentum equation. So we take the same scheme here, we distribute it out, and if you want, you can reference the Jacobi identity and some more of those other fantastic feats. But here, we're just going to use the distributivity law, again, with this operator after we already put it in the transformation style. The Hamiltonian and the time evolution operator go to 0 again. Wonderful. So we're left really with just applying what it is to P and the Hamiltonian and the commutator. And if you remember from chapter 3, we saw what that was too. So let's get back and simplify. All right. So recalling that then that the Hamiltonian was P squared over 2m and plus V. Okay, we're cool there. Put it in, use linearity as we've shown in problem 3.14. And then, of course, from there, we see that P and P squared commute. So you just end up with P cubed minus P cubed. So, of course, that goes to 0. No problem there. But we did see in problem 3.14 part C what it was to have a scalar and the momentum operator acting on some test function, and we saw that that led us to a IH bar df dx. But here, since we reversed the order, we used the anti-symmetric nature of the commutators, right, to put a negative sign, and that's why we have one here. Okay. But nonetheless, we see that this IH bar cancels with that one, so we're good, and we get the negative dv dx. This is exactly the differential equation for the momentum equation. And we see that we get the exact same equations from the classical point of view. Okay, the derivative of momentum gave us a force equation with time, right? So this gave us the F equals ma, F equals ma style term, because everything was related to the negative gradient of the potential. That's a lowercase f. So yeah, we have this under reps. That's pretty darn cool. Then of course we have here something that looks like mv equals momentum. So this is a fascinating result and a fascinating way of relating quantum to classical, and we see that the observables themselves change with time, not the wave function. How cool is that? I think this is fascinating. But again, we have to be careful because of the ramifications of the different pictures. One of them is better suited for certain scenarios, not all scenarios. So be aware that toolbox is steadily growing and it's going to be a lot to keep track of. So to summarize, we saw once again how the Heisenberg system or Heisenberg picture relates and mirrors classical physics pretty well. However, again, we have to be careful on how to maneuver with them because it's not always the easiest case on how to see a path, and those commutator relations keep popping up. They are never not going to pop up from pretty much here on out because they tell us the behavior of the system. Again, whenever you have commutables and the commutator relation equals 0, then you can have some technical maneuvering that's there. Be aware of those properties because they do hold a very special place in the theory. The commutator algebra relating to the group theory and representations, things like that will be very important moving forward. But that being said, a massive thank you needs to go out to all my supporters, especially the ones that keep me steady on this goal. I think it's turning into a lot more fun now that we're getting into some nuance of the material, not just, random calculations, but we're seeing how those things are starting to play a bigger part of the theory. So I'm really glad that this new edition has this chapter. But, again, just to let everybody know, I'm very grateful for everything that you've done and all the support and weird late night messages when I get an idea. Definitely appreciate you hearing me out. If you'd like to see more about this and the process, you can also become a patron for access to supplemental material, current and future projects, and one-on-one help. New content is posted daily at this point to fuel your curiosity, so you can definitely have a large library to reference by the end of the year. Books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. As always, thank you for watching, and until next time, stay curious.